Welcome back, chemistry students. In this next video, we are going to be forging ahead onto pages 465 to 473 in your Apologia Chemistry book. I recommend having it available during the lecture if you'd like to follow along there. We'll be covering examples 13.4 and 13.5, and on your own's 13.6, 7, and 8. So we're looking at the change in energy or the enthalpy in different chemical reactions, and in this section we'll be applying enthalpy to stoichiometry. And our first example at the bottom of page 465 reads, we determined previously that the change in H, which is at standard conditions, for the combustion of ethyl alcohol is negative 1,236 kilojoules. How much energy can be produced by burning 150.0 grams of ethyl alcohol in excess oxygen? So our ears should always perk up, right, when we're given gram units. We know at some point we're going to have to be changing them to moles when we're talking about stoichiometry. But let's start here. First, they start with a very good equation that's balanced. We have the ethyl alcohol here is combined with oxygen in a combustion reaction, and again we produce carbon dioxide and water. And then we we had determined in the previous problem on the previous page that the delta H for that is a negative 1,236 kilojoules. So since it's negative, we know it's an exothermic reaction and that this energy should be added to the products. So we've updated our equation by adding it here on the right side. Next, we want to convert the grams of ethyl alcohol to moles. So you would have to go ahead and calculate the AMU for C2H6O, which ends up being 46.1 grams per mole, or AMU. And we multiply this conversion factor by the number of grams that we were provided with at the beginning of the problem. So we've determined we have 3.25 moles of the C2H6O. Now, we know that according to our equation, it's 1 mole of this ethyl alcohol, right, or we can start here, will give us this number of kilojoules of energy, 1,236. Therefore, that provides us with enough information to make another conversion factor. We have the number of kilojoules per mole, and we can multiply that times the number of moles that we have, that we were provided with after we converted from grams. And then that gives us the total number of kilojoules if we had this number of moles to start with. All right, let's look at a similar problem. That's the next one in this example. It says one way of producing butane, which is C4H10, for cigarette lighters is to force ethane to react with itself. And so we have this equation here. 2 times the C2H6 yields C4H10 plus hydrogen gas. So it says if you have 1.23 kilograms, and notice it's not in grams, so we're probably going to have to do a conversion along the way. If we have 1.23 kilograms of ethane and we want to turn it all into butane, how many kilojoules of energy would be necessary? All right, so our first step is we want to calculate the delta H at standard conditions for this equation. And we're using Hess's law. So we will be working with the values on this chart for various enthalpies for various molecules. So, and we always start with the with the products in this equation. We will multiply this imaginary 1 here, right, times the value for the C4H10 taken off that chart that I just referenced. In addition, the hydrogen gas, which is naturally found as H2, is always 0 because that's in its elemental state, so that becomes a negligible value. And then we subtract the value of the reactant. Here we have 2, so we have 2 moles, and then again times the value you would have retrieved off that table for C2H6. And then once this is all calculated, you have a positive 43 kilojoules. Since it's positive, that's an endothermic reaction, and that energy would be included in the reactants on the left side of this equation. All right, so now we're move ahead. We know we were given information in kilograms. That will have to be converted to grams, so it ends up being 1.23 times 10 to the third grams. And we need to change the grams into moles. So again, you would calculate the AMU for C2H6, which is 30.1, and then multiply it by this conversion factor, moles over grams. That helps to eliminate these units here, and you know you have 40.9 moles of C2H6. Then you use this. You look back at your chemical equation, you see that you have for every 2 moles of your reactant, you're working with 43 kilojoules. And that can create another conversion factor because you're asking the question, well, if I need 43 kilojoules to react with 2 moles, how many kilojoules would I need to react with 40.9? So you multiply the 40.9 times this conversion factor, the 43 over the 2 moles, and you get a total of 880 kilojoules for that answer. All right, so now let's look ahead at your on your own 13.6 on page 467. And in this case, I've outlined the steps once again. It's a very, very similar problem, but I've outlined the steps here. We're going to start with the balanced equation, calculate the delta H, add the energy to the equation, convert grams to moles, and then calculate the amount of energy released for that number of moles. So here comes our question. Ethane gas, C2H6, has also been considered as a fuel for automobiles because, like octane, it releases a lot of energy when it's burned. How many kilojoules of energy are released when 250 grams of ethane undergo complete combustion? So we remember with complete combustion, we start with our reagent here, the ethane. It reacts with oxygen. We have carbon dioxide and water as our products. We calculate this delta H by using Hess's law, starting again with our products and using our handy dandy table here. And so here we have 4 times the value of CO2 on the table, which is a negative 394 kilojoules per mole. And here we have the 6 times the water. Make sure you notice the water's in the gas state because it's different than the liquid, but it's going to be 6 times the negative 242. So that wraps it up for our products. Then we're going to subtract the value for the reactants. You have 2 times the value for C2H6 off the chart. And then finally, this is negligible because the O2 is found in its elemental state, and this is going to be 0, and so they didn't even include it on here. All right, so we have products minus reactants. We have a negative 282,859 kilojoules. Since it's negative, it's exothermic, and it's going to be added to our products. So we've added this energy up here on this original equation over on this side. Now we need to convert our 250 grams to moles by calculating the AMU for the C2H6, which is 30.1 grams per mole. We multiply the 250 times our conversion factor, and we find that 250 grams equals the same as 8.31 moles. Now finally, we know that if we had 2 moles was yielding this number of kilojoules, we're asking, all right, well, how many would 8.31 yield? So we're multiplying the 8.31 times this special conversion factor, 2 over the 2,859, and then our answer here is 1.19 times 10 to the 4th kilojoules. All right, the next on your own is the same process. We're going to work with a balanced equation, calculate the delta H for the equation, add energy to the equation, convert grams to moles, and then calculate the amount of energy released for that specific number of moles. So it says, when mined, coal has a small amount of sulfur in it. When that coal is burned in a power plant, the sulfur burns right along with it, producing SO3 gas. When the SO3 gas, that sulfur trioxide, reacts with the water in the air, it produces sulfuric acid according to the following equation. The sulfuric acid produced in this manner falls to the earth as acid rain. How much energy is produced when 50 grams of H2SO4, that's sulfuric acid, are produced in this way? So we're starting with the water plus the sulfur trioxide, and it's in this reaction, it's yielding the sulfuric acid H2SO4 in a liquid state. Calculate the delta H. Again, we would go back to this chart, right? We have to find these values like the H2SO4. We start with our reactants. So we had an imaginary 1 here. It's 1 times the value off that chart for H2SO4. That's it for our products. Then we subtract our reactants, right? We have 1 times the value for water in the gas state, and 1 times the SO3 in the gas state, and after everything's calculated, we have negative 173 kilojoules. Since it's negative, it's going to be exothermic, and we add it to the product side, and that's goes here. Now we're given that we had 50 grams, so we have to convert grams to mole by computing the AMU for H2SO4, which is 98.1. So we multiply the grams times this conversion factor, which is basically the same as dividing it by the AMU of 98.1, and you know you have 0.51 moles. So our question is, if 0.51 moles of H2SO4 is yielded with 176 kilojoules, how much would 0.51 moles yield? And so we multiply it by this conversion factor, the 176 over the 1, and we get 89.8 kilojoules. All right, now moving on to energy diagrams. This is a way to visualize the delta H, or the change in energy, over the course of a chemical reaction. So it can help us, if it has units on it, it can help us quantitate the delta H, and also perhaps if there was a time unit here, it could also help us know the amount of time that it would take to complete a reaction. So in this particular reaction, right, we have the ethanol reacting with hydrogen gas, and then our products are the ethane, C2H6, plus the H2O. So some of the things that we're looking at here first are the difference in the energy level between the reactants, or this side of the equation, versus the products were here at this side. So we're starting at 100 and we're dropping down to 50. That's a negative delta H, and so therefore this tells us it's an exothermic reaction. Also, this window here between the initial level and then the peak of the reaction shows us that it requires what's called an activation energy. It's the energy necessary to start a chemical reaction. And what's interesting from biology is that when we work with enzymes, these specialized proteins, enzymes help to reduce the activation energy in certain reactions in our bodies. All right, so again, exothermic reaction, our reactants sort of start high and end up low. We're going to compare and contrast that to the endothermic. Here, our reactants start low, but the products end high. So here we have a high activation energy, and then our delta H here ends up being positive because it's here like it started at 20 and it ends up at 50. All right, let's look at this example in your book. I'm guessing it's about page 470. You can consider these various energy diagrams. So it says, which diagram represents the most exothermic reaction? All right, so we remember, based on this, right, on exothermic it should start high and end low. So we're saying which one of these starts high and ends low. So we could pick from either 1 or 3. Either one of those could actually be exothermic. However, it's asking which is the most exothermic and exactly what is the delta H. So in this one, it's going from 100 down to 50. So our delta H would be negative 50. And this one's just going from 50 to 25. So I'd say number 1 wins on this one. It's got a bigger delta H of negative 50, and that's the answer here. It says which represents the reaction that's easiest to get started. So that would have the lowest activation energy, and that would be this one here. It has the smallest increase from the peak from the reactants. So number 3 is the match for that. And then finally it says what represents an endothermic reaction. Well, we know endothermic, the reactants are low, the products are high. And so the delta H on this, it's going from 20 to approximately 40. So it looks like it would be about 20 kilojoules on that. All right, so on your own, page 471, we're on 13.8. They're going to ask you for to create your own chart. Of course, the answers are in the back, but you can just think of how you would create a diagram to match this scenario. And so on A, it says this reaction is very hard to start, but once it gets started, it gets very, very hot. So we know if it's hot, it's got to be exothermic. So you could draw something like this. It would be where our reactants are higher than the products. So it has sort of a steep slope going down here. It says it's very hard to start. So we have some activation energy necessary. And that's probably the best match for A. Then on B, it says this reaction is incredibly easy to start, but it gets only slightly warmer than before you began the experiment. All right, so on here we have a small activation energy, and then it does drop down, so it does get warm, but there's not a drastic difference between the energy level of our reactants and our products. All right, let's look at C and D. See, it says this reaction is hard to start but gets slightly cold during the reaction. So here I drew this one. It is hard to start, so it would have a high activation energy, but because it's cold, we still have our products being higher than the initial energy level of the reactants. And then finally on D, it says this reaction is easy to start and gets very, very cold during the reaction. So here we have a higher activation. Well, it says relatively easy, so maybe I made this a little too high. But anyway, you'd have a relatively low activation energy. And then the products, because it gets cold, then your products are going to be higher than your reactants. And that would represent an endothermic reaction. Okay, so now next we're moving on to discuss the concept of entropy. It's a measure of the disorder that exists in any system. So I'm sure any of us could relate to this concept, how things just become disordered in our lives. I know this could possibly be a picture of my own living room at times. We can all relate to disorder. But in this particular chapter, we are given units of disorder, which is quite interesting. And so the energy units for entropy are various energy units. It could be joules, kilocals, or kilojoules, then divided by moles times Kelvin. So when we have high entropy, we have high levels of disorder, and low entropy means things are not disordered. So the next time your parents want you to clean your room, right, that maybe they'll give you your room an entropy score. So let's talk a little bit about states of matter and how entropy applies to them, in addition to the second law of thermodynamics. So we know on that second law, right, it says the entropy of the universe must always either increase or remain the same. It can never decrease. And since that's a scientific law, it's been tested many, many times. But we can look specifically at states of matter. We know that solid state has the least amount of entropy associated with it. In other words, the molecules stay ordered compared to the liquid state, where the molecules are moving around more and it has a higher state of entropy. And then finally, the gaseous state is the highest, and the molecules are moving around so randomly and so quickly that the entropy is quite high in that state of matter. Then some of the points the book points out is the entropy of a system increases with increasing temperature. So that makes sense, right? That's consistent with these. Going from a solid to a liquid to a gas, you can imagine that as you're increasing temperature on something like ice to water to gas, as you're increasing the temperature, the entropy would increase. And then it also says the entropy of a system increases as the matter it contains increases. So, for example, as your room gets more and more stuff in it, right, the amount of disorder increases. So that makes sense, right? The more matter that's in your room, the more that the disorder grows. And then finally, on page 473, we have mention of this equation 13.4. We have another letter introduced here, the letter S, that stands for entropy. And so chemists will often look at the change in entropy, and this particular equation is pertinent, right? We know the change in S of the universe has to be greater than or equal to 0, and that reflects sort of a mathematical equation to that second law of thermodynamics. In our next video, we'll be looking at some more examples, and so I encourage you to stay tuned.